Welcome to today's walkthrough of LeetCode problem number 743, Network Delay Time. In this problem, we'll explore how to calculate the time it takes for a signal to travel through a network of nodes. We'll break down the problem, consider possible approaches, and review the most efficient solution. Let's dive in. In this problem, we're working with a network of n nodes, labeled from 1 to n. The network is represented by a list of directed edges, where each edge has a starting node U, an ending node V, and a travel time W. The key task is to send a signal from a given starting node K, and we need to determine the time it takes for the signal to reach all the nodes in the network. If some nodes cannot be reached, we return -1. For the input format, we're given the number of nodes n, the list of directed edges times, and the starting node K. The output is a single integer that represents the minimum time for the signal to reach all nodes, or -1 if not all nodes are reachable. Let's consider an example to understand the problem better. Suppose n equals 4, the list of edges is 2, 1, 1, 2, 3, 1, 3, 4, 1, and the starting node is k equals 2. The signal begins at node 2. It takes 1 unit of time to reach node 1 via the edge, 2, 1, 1, and another 1 unit of time to reach node 3 via the edge, 2, 3, 1. From node 3, the signal takes an additional 1 unit of time to reach node 4 via the edge, 3, 4, 1. The longest time it takes for the signal to reach any node is 2, so the output for this example is 2. Here's another example. If n equals 2, the list of edges is 1, 2, 1, and the starting node is k equals 2. The signal starts at node 2, but there are no outgoing edges from this node. This means the signal cannot reach node 1, making it impossible for all nodes to receive the signal. Therefore, the output in this case is -1. This illustrates the scenario where the graph is disconnected, and not all nodes are reachable from the starting node. In one more example, let's say n equals 3, the edges are 1, 2, 1, 2, 3, 2, and the starting node is k equals 1. The signal starts at node 1 and takes 1 unit of time to reach node 2 via the edge, 1, 2, 1. From node 2, it takes an additional 2 units of time to reach node 3 via the edge, 2, 3, 2. The longest time it takes for the signal to reach any node in this case is 3, so the output is 3. To solve this problem efficiently, we must consider a few key observations. First, this is fundamentally a shortest path problem, which can be tackled using algorithms like Dijkstra's algorithm or the Bellman-Ford algorithm. Dijkstra's algorithm, when implemented with a priority queue, is particularly well suited to handle larger graphs efficiently. Additionally, the constraints require us to consider edge cases like disconnected graphs, single-node networks, and scenarios with multiple paths to the same node, where only the shortest path matters. Finally, the solution should scale efficiently for the upper limits, where n can be as large as 100 and the number of edges can go up to 6,000. To solve the network delay time problem, the objective is to calculate the time it takes for all nodes in a network to receive a signal sent from a starting node. Several approaches can be considered for this. The brute force approach uses simple breadth-first or depth-first search to traverse all reachable nodes, updating the minimum delay for each node. This process is repeated iteratively for all nodes. While this method is straightforward, it has a high time complexity of O(n squared) for dense graphs, making it inefficient when the number of nodes and edges is large. Another option is the Bellman-Ford algorithm, which is well suited for weighted graphs, even those with negative weights, though this isn't applicable here since the weights are strictly positive. Bellman-Ford works by relaxing all edges iteratively up to n1 times, where n is the number of nodes. While more efficient than brute force, with a time complexity of O(n*e), the iterative edge relaxation makes it slower compared to other algorithms when dealing with graphs having only positive weights. Dijkstra's algorithm provides a more optimized approach for this problem. By leveraging a priority queue, it efficiently finds the shortest path from the starting node to all other nodes in the graph. The algorithm repeatedly processes the node with the smallest known distance, updating its neighbors' distances and pushing them into the priority queue as needed. This ensures that nodes are prioritized in the order of their shortest delay, minimizing unnecessary computations. With a time complexity of O(n+e*log en), Dijkstra's algorithm is faster than Bellman-Ford when all edges have positive weights, as it avoids iterative edge relaxation. The priority queue plays a crucial role here, as it allows for efficient extraction and updates. For this problem specifically, the graph's characteristics weighted, directed, and strictly positive weights make Dijkstra's algorithm the ideal choice. Its balance of efficiency and simplicity, combined with its ability to minimize redundant computations, provides a clear advantage over brute force and Bellman-Ford. While implementing a priority queue adds some complexity, the performance benefits far outweigh this trade-off. For the implementation, it's recommended to represent the graph as an adjacency list for efficient traversal. A min-heap, or priority queue, will be used to prioritize processing nodes with the smallest delays. Additionally, tracking visited nodes is important to prevent redundant processing and ensure correctness. If not all nodes can be reached from the starting node, the solution should return -1, as specified in the problem. From a complexity standpoint, the time complexity is O, n plus e, asterisk log n, where n represents the number of nodes and e the number of edges. This accounts for both the adjacency list traversal and the priority queue operations. Space complexity is O, n plus e, which includes storage for the adjacency list and the additional space required by the priority queue. These considerations ensure the solution is both efficient and scalable for large graphs. The network delay time problem challenges us to find the time it takes for a signal to propagate from a given starting node to all other nodes in a directed, weighted graph. If any nodes remain unreachable, the result should be -1. To solve this efficiently, we'll use Dijkstra's algorithm, which calculates the shortest path in a graph. First, we need to parse the input. The times list represents edges as u, v, w, where u is the source node, v is the target node, and w is the weight or time to travel between them. We're also given n, the total number of nodes, and k, the starting node. Next, we'll represent the graph using an adjacency list. This is a dictionary where keys are nodes and values are lists of tuples representing neighbors and their weights. For instance, if times equals 1, 2, 1, 2, 3, 2, 1, 3, 4, we'll construct the graph as 1, 2, 1, 3, 4, 2, 3, 2, 3. This representation is efficient for sparse graphs and will allow us to traverse the network effectively. To begin Dijkstra's algorithm, we need to set up a few key data structures. First, we use a min-heap, or priority queue, to ensure nodes with the shortest known distances are processed first. This is critical for the greedy nature of the algorithm. Next, we initialize a dist dictionary to store the shortest distance from the starting node k to every other node. All distances are initially set to infinity, except for k, which is set to 0. For example, if n equals 4 and k equals 1, the initial distances would be 1 o'clock, 2, inf, 3, inf, 4, inf. Now, we push the starting node into the heap as 0, k, to mark it as the first node to process. The main steps of Dijkstra's algorithm involve repeatedly extracting the node with the smallest distance from the heap. For each node, we check its neighbors in the adjacency list. If traveling to a neighbor results in a shorter distance than previously recorded, we update the distance and push the neighbor into the heap. This ensures that the shortest paths are calculated incrementally as we process nodes in order of increasing distance. Once all nodes have been processed, the longest distance in our dist dictionary represents the time it takes for the signal to reach every node. If any node still has a distance of infinity, it means that node is unreachable, and we should return -1 as the result. Dijkstra's algorithm works effectively here because it processes nodes in order of their distance from the source, thanks to the min-heap. This guarantees that we always find the shortest path to each node. The algorithm's use of a priority queue ensures efficiency, even for graphs with many nodes and edges. It's also important to consider edge cases. For instance, in a disconnected graph, unreachable nodes will lead to a result of -1. If the graph contains only a single node, the result is always 0 because the signal starts and ends at the same place. Lastly, when there are multiple paths to a node, the algorithm's greedy approach ensures the shortest path is always chosen by comparing distances during each iteration. The data structures used in this algorithm play a crucial role in its efficiency. The adjacency list is a compact and memory-efficient way to represent sparse graphs, requiring only O(e) space, where e is the number of edges. The min-heap allows us to extract and insert nodes efficiently, with each operation taking O log v, where v is the number of nodes. The DIST dictionary tracks the shortest distances to each node, with all nodes initialized to infinity except for the starting node. For the complexity analysis, the algorithm's time complexity is O, V plus E, log V. Building the adjacency list takes O, E, and each node is processed once, relaxing edges using heap operations that take O, log V. The space complexity is O, V plus E, with the adjacency list requiring O, E, and the distance dictionary and heap requiring O, V. These complexities make the algorithm well-suited for large graphs with many nodes and edges. Let's walk through an example to solidify our understanding. Suppose the input is times equals 2, 1, 1, 2, 3, 1, 3, 4, 1, with n equals 4 nodes and the starting node k equals 2. First, we build the adjacency list, 2, 1, 1, 3, 1, 3, 4, 1, 1, 4. Next, we initialize the DIST dictionary as 1, ANF, 2 o'clock, 3, ANF, 4, ANF, and the heap as 0, 2. Now, we process nodes in the heap. We pop 0, 2, and update distances to its neighbors, resulting in DIST equals 1, 1, 2 o'clock, 3, 1, 4, INF, and heap equals 1, 1, 1, 3. Next, we pop 1, 1, but find no updates. Then, we pop 1, 3, and update the distance to node 4, giving DIST equals 1, 1, 2 o'clock, 3, 1, 4, 2, and heap equals 2, 4. Finally, we pop 2, 4, with no further updates. The maximum distance in DIST values is 2, so all nodes receive the signal in 2 units of time. The output is therefore 2. To solve the network delay time problem, we start by importing the heap module, which will help us efficiently manage a min heap. Within the network delay time function, we first create an adjacency list to represent the graph. This list maps each node to its neighbors and the associated time weights for traveling to those neighbors. The adjacency list is initialized as a dictionary where each node from 1 to n has an empty list, and we populate it by iterating through the times input. Each edge from node U to V with weight W is added to the graph. Next, we initialize a min heap with a tuple containing the starting time of 0 and the source node k. We also create a shortest underscore time dictionary to record the minimum time required to reach each node. Then, we enter a while loop to process nodes in the heap. On each iteration, we pop the node with the smallest time. If this node has already been processed, we skip it. Otherwise, we record the time taken to reach this node in the shortest underscore time dictionary. After that, we explore the current node's neighbors and calculate the time to reach each one. For each neighbor that hasn't been processed yet, we push a new tuple onto the heap. This tuple contains the updated time, which is the current time plus the weight of the edge leading to the neighbor, and the neighbor itself. This allows us to prioritize the shortest times as we continue processing the heap. After the heap is empty, meaning all reachable nodes have been processed, we check whether the shortest underscore time dictionary contains all n nodes. If it does, we return the maximum time recorded in shortest underscore time, as this represents the longest delay among the reachable nodes. If not all nodes are reachable, we return -1 to indicate that it's impossible to send a signal to every node from the starting node. This implementation ensures an efficient solution using Dijkstra's algorithm with a time complexity of O, E log V, where E is the number of edges and V is the number of nodes. Here, we start by defining the network delay time method, which takes in the times array representing the edges, n as the number of nodes, and k as the starting node. The first step is to create an adjacency list to represent the graph. We use a hash map where each key is a node, and the value is a list of its neighbors, represented as an array containing the destination node and the travel time. We initialize the graph by adding an empty list for each node, and then populate it using the times array. Next, we set up a priority queue, or min heap, to process nodes in order of their travel times. Each entry in the heap is a pair containing the current time and the node. Initially, we add the starting node k with a travel time of 0. To keep track of the shortest time to reach each node, we use another hash map called shortest time. As we process nodes, the main loop begins by pulling the node with the smallest travel time from the heap. If this node has already been processed, we skip it, ensuring we don't revisit nodes unnecessarily. If the current node hasn't been processed yet, we record its shortest travel time in the shortest time map. Then, we explore its neighbors by iterating over the adjacency list for this node. For each neighbor, we calculate the new travel time as the current node's time plus the edge weight. If the neighbor hasn't been processed yet, we add it to the heap with its updated travel time. This allows us to continue exploring nodes in order of increasing travel time. After processing all reachable nodes, we check if the size of the shortest time map matches the total number of nodes, n. If not, it means some nodes are unreachable, and we return -1. Otherwise, we compute the maximum travel time from the shortest time values and return it as the result. This ensures the output is the time it takes for all nodes to receive the signal, or -1 if that's not possible. To solve the network delay time problem, we start with a simple example. The input consists of a list of edges, where each edge specifies a source node, a target node, and the time it takes to travel between them. Here, times is given as 2, 1, 1, 2, 3, 1, 3, 4, 1, meaning node 2 connects to nodes 1 and 3 with travel times of 1 each, and node 3 connects to node 4 with a time of 1. We also have n equals 4, indicating there are 4 nodes in total, and k equals 2, which specifies node 2 as the starting point. The first step is to construct the graph using an adjacency list. Initially, we set up an empty list for each node, 1, 2, 3, 4. Then, we process each edge in times, adding 1, 1, and 3, 1 to node 2, and 4, 1 to node 3. This results in the graph representation 1, 2, 1, 1, 3, 1, 3, 4, 1, 4. Next, we apply Dijkstra's algorithm to find the shortest path from the starting node. We initialize the heap with the starting node and a time of 0 as 0, 2, and create an empty dictionary shortest underscore time to store the minimum time to reach each node. The algorithm proceeds by iteratively processing nodes based on their travel times. The first iteration begins by popping the top element from the heap. This gives us 0, 2, meaning we are visiting node 2 with a current travel time of 0. We mark node 2 as visited by adding it to shortest underscore time, so now shortest underscore time equals 2 o'clock. Next, we look at its neighbors. From the graph, node 2 connects to node 1 with a time of 1 and to node 3 with a time of 1. We push these neighbors into the heap, resulting in heap equals 1, 1, 1, 3. In the second iteration, we pop 1, 1 from the heap, indicating we are visiting node 1 with a travel time of 1. Node 1 is marked as visited, updating shortest underscore time to 2 o'clock, 1, 1. In the third iteration, we pop 1, 3 from the heap, visiting node 3 with a time of 1. Similarly, we mark node 3 as visited, shortest underscore time equals 2 o'clock, 1, 1, 3, 1. For node 3, we see it has a neighbor, node 4, with a travel time of 1. Adding this to the heap gives us heap equals 2, 4. Finally, in the fourth iteration, we pop 2, 4 from the heap, visiting node 4 with a total time of 2. Marking node 4 as visited updates shortest underscore time to 2 o'clock, 1, 1, 3, 1, 4, 2. At this point, all nodes have been visited. Now that we've visited all the nodes, we move on to the final step. We calculate the maximum value in the shortest underscore time dictionary, which represents the time it takes for the signal to reach the farthest node. In this case, the maximum time is max 0, 1, 1, 2 equals 2. Since all nodes are reachable, the output is 2. Next, we consider a different scenario where the graph is disconnected. For example, if times equals 1, 2, 1, n equals 3, and k equals 1, we notice there's no connection to node 3. The graph is initialized as 1, 2, 3. Processing the edge adds 2, 1 to node 1, resulting in 1, 2, 1, 2, 3. Using Dijkstra's algorithm, we start from node 1 with heap equals 0, 1, and an empty shortest underscore time dictionary. In the first iteration, we pop 0, 1 from the heap, visiting node 1 with a travel time of 0. Marking node 1 as visited updates shortest underscore time to 1 o'clock. We then look at its neighbor, node 2, which is reached with a time of 1. Pushing this into the heap gives us heap equals 1, 2. In the second iteration, we pop 1, 2 from the heap, visiting node 2 with a travel time of 1. Marking node 2 as visited updates shortest underscore time to 1 o'clock, 2, 1. At this point, the heap is empty, and we check whether all nodes have been visited. Here, node 3 remains unreachable, as it is not in the shortest_time dictionary. This means not all nodes can receive the signal. As a result, the output is -1, indicating that the graph is disconnected. Lastly, consider the simplest case of a graph with a single node. In the single node example, the times list is empty, n equals 1, and k equals 1. This means there is only one node, and it is the starting point. The graph is initialized as 1. Applying Dijkstra's algorithm, we start with heap equals 0, 1, and an empty shortest_time dictionary. In the first iteration, we pop 0, 1 from the heap, visiting node 1 with a travel time of 0. Marking node 1 as visited updates shortest_time to 1 o'clock. With no other nodes to process, we check whether all nodes have been visited. Since there is only one node, it is considered visited. The maximum travel time is max 0 equals 0, as the starting node has no delay. Thus, the output for this example is 0. The time complexity of our solution is driven by Dijkstra's algorithm, which relies on a priority queue implemented as a min-heap. To break it down, we start with graph construction. Here, we build an adjacency list by iterating over the times input, which takes time where e represents the number of edges in the graph. Next, we focus on operations involving the heap. The main loop processes nodes until the heap is empty. In the worst case, each node is processed once, and during this time, all edges are considered. Removing the smallest element from the heap, an operation known as heap.heapPop, takes log v, where v is the number of nodes. Similarly, adding a new element to the heap, or heap.heapPush, also takes log v. Since each edge is examined only once, we perform at most push and pop operations, making the total time for heap operations plus v, log v. After processing the graph and heap operations, we perform a final check to determine the maximum delay time. This involves computing the maximum value in the shortest_time dictionary, which takes v, time. Combining all these steps, the overall time complexity becomes log v plus v log v plus v, which simplifies to plus v log v. Now, let's analyze space complexity. First, representing the graph as an adjacency list requires space, as we need to store all edges. Next, the heap, which at most contains all nodes, uses v space. Lastly, the shortest_time dictionary stores the shortest delay time for each node, requiring v space as well. When we combine these components, the total space complexity comes out to plus v. To understand the efficiency of this approach, let's compare it to a naive solution. A brute force method, such as Bellman-Ford, would repeatedly relax all edges for up to v1 iterations. This leads to a time complexity of v*e, which is slower, especially for dense graphs, and a space complexity of e plus v. In contrast, our implementation with Dijkstra's algorithm leverages a priority queue to optimize edge relaxation and minimize updates. This results in a faster time complexity of e plus v, log v, for sparse graphs while maintaining the same space complexity of e plus v. Analyzing the best, average, and worst cases provides further insights. In the best case, where all nodes are directly connected to the source node, the algorithm processes only v1 edges, yielding a time complexity of v log v. For an average sparse graph, the algorithm processes e edges, leading to a time complexity of e plus v log v. In the worst case scenario, such as a fully connected graph with e equals v*2 edges, the complexity grows to v squared log v. The mathematical justification for the big O notation lies in the dominance of heap operations, which depend on the logarithmic factor of the number of nodes. Since each edge is processed at most once, the overall complexity remains bounded by e plus v log v, regardless of the specific case. When solving the network delay time problem, there are some common mistakes you should avoid. First, using Dijkstra's algorithm without a priority queue is a frequent error. Instead of iterating through all nodes to find the minimum distance, which results in an inefficient n squared time complexity, you should use a priority queue to achieve n plus e log n, making the algorithm much faster for larger graphs. Another common pitfall is not initializing distances correctly. It's crucial to set the starting node's distance, k, to 0 and all other nodes to infinity. Failing to do this can lead to incorrect results, as some nodes may never be processed. Additionally, some forget to account for disconnected nodes, assuming all nodes are reachable. If any nodes remain unvisited, the correct result is -1, not the maximum distance of processed nodes. Lastly, make sure to process edges in the correct direction. Since the graph is directed, treating it as undirected will result in errors. Always follow the direction specified in the input. Another mistake to watch out for is overcomplicating the graph representation. Using overly complex or inefficient data structures can make your code harder to debug and slower to execute. A simple adjacency list is typically the best choice for this problem, as it keeps the implementation clean and efficient. Now, let's turn to interview-specific insights. This problem is fundamentally about finding the shortest path in a weighted, directed graph. Interviewers often test your knowledge of when to use algorithms like Dijkstra or Bellman-Ford. Be prepared to discuss edge cases such as disconnected graphs, single-node graphs, and those with zero-weight edges. You should also be ready to analyze the time complexity of your solution. For Dijkstra's algorithm with a priority queue, the complexity is O(n plus e) log n, which is efficient for sparse graphs. Lastly, be clear about the trade-offs between Dijkstra and Bellman-Ford. While Bellman-Ford handles negative weights, this problem explicitly states that edge weights are positive, so Dijkstra is the better choice. If you want to explore related problems, there are several on LeetCode that build on similar concepts. For example, problem number 787, cheapest flights within k stops, adds a constraint on the number of stops while finding the shortest path. Another is number 1631, path with minimum effort, which applies a Dijkstra-like approach to a grid instead of a traditional graph. Problem number 1514, path with maximum probability, changes the focus to maximizing probabilities rather than minimizing distances, showcasing how the same algorithmic framework can adapt to different goals. Finally, there's number 997, find the town judge, which simplifies the graph problem to focus on node relationships rather than weights. These variations are great for honing your understanding of graph algorithms and their adaptability to different scenarios. There are also alternative approaches to consider, each with its own trade-offs. The Bellman-Ford algorithm, for instance, handles graphs with negative edge weights, but its O(n*e) complexity makes it slower for dense graphs. While not relevant to this problem due to the absence of negative weights, it's a good option to keep in mind for other scenarios. The Floyd-Warshall algorithm, on the other hand, provides all pairs' shortest paths, but its O(n)³ complexity makes it impractical for large graphs. It's most useful when you need to repeatedly query shortest paths between many node pairs. Lastly, there's the DFS with backtracking approach, which explores all possible paths. However, it's highly inefficient for large graphs, as it can lead to exponential complexity. This method is rarely used for shortest path problems unless the graph is very small or constraints are exceptionally tight. These alternatives highlight the importance of selecting the right algorithm for the problem at hand. Great job making it to the end. Today we covered LeetCode problem number 743, network delay time. We explored the use of Dijkstra's algorithm to solve this problem efficiently, highlighted key takeaways, and discussed edge cases to consider. Thanks for watching, and don't forget to like, subscribe, and keep practicing your coding skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!